Thank you for joining our talk on enterprise domain-driven design for real-time ubiquitous distributed data. My name is Laura Schornack, and I will be presenting with my Northern Trust colleague, Maureen Penzenik, today. And the opinions that we are expressing are our own and not necessarily those of Northern Trust. Throughout my career as an IT architect, I have led many domain-driven design exercises. I am a very big proponent of using EDDD. However, these have been in the application world, and they've been used to break down monoliths into right-sized components, creating a more distributed architecture that results in more resilient applications. However, there has not been much conversation in doing this in the data space and the data analytics space. So Maureen and I are excited to show you the merging of these two worlds.
That's right, Laura. Thanks. I've been in the IT business for many years, mostly devoted to data warehousing and analytics technologies. So data has been my passion, and making data available and meaningful to business people through the use of innovative technologies such as Kafka really pretty much sums up my career.
Let's start by reviewing our agenda a little bit. Our talk today will start with a description of the problem we are trying to solve, and a summary of the past attempts that the industry has taken to solving this problem, especially in the application space. However, this solution is usually looked at as a tool only for applications and just one application. So then we'll talk about how enterprise domain-driven design takes this to a different level and allows data sets to be shared across the whole enterprise. Then we'll walk through a quick hello world example and give an explanation of how you can use this to apply to event storming. And then after that, we'll talk about how this can be applied in an ecosystem that is wider than just one application, where it becomes enterprise domain-driven design.
Right, and then we'll discuss how domain-driven design is not just for applications, but how it can be applied to data analytics environments and explore some of the differences as well.
Let's start by reviewing what we want. We want to cut our application delivery time by not redoing all of the work, every single project. We want to get off the hamster wheel of recreating our data sets. If data sets are used in one project and in one application, and if they have the same context as they would in the next project and the next application, there is no need to redo this work time and time again. The problem is that data sets cannot be sourced and created from different applications with the expectation that their boundaries will remain the same. Recreating a data set in a different application is like recreating a second data set. And then you have two different data sets when really you should just have one. So this creates a lot of issues. For example, errors. Recreating data causes more errors. It stands to reason that if you're repeating the same work in each application, you will wind up with more errors in that data set than if you had just reused the previous data set. Twice the work, twice the errors. Our next issue is inconsistency. A data set will be inconsistent if it is created multiple times by multiple people, across multiple projects, across multiple applications. And then you'll have to do a lot of reconciliation activities to remove this inconsistency later. This causes a lot of technical debt, exponential amount of technical debt. At the end, to clean it up, you'll have to collapse all of your data sets that were separately created into one. And that's a lot more expensive than just doing it right the first time. Another issue is that you'll have a reactive approach to data problems. Fire calls, emergency production issues are very expensive, and these could be prevented if you control what data is coming in and out of your applications, and which brings us to access and audit issues as well. From having unidentified duplicates of the same data or errors introduced into a data set that was fine in a different application. So if the data has consistent definitions, it should be used consistently in the same way across all applications. Duplicate data consumed by downstream applications will not be fit for purpose.
Exactly, Laura. And this results in not only inconsistencies of business definitions of the data between applications, but also with the downstream consumers of data, such as those for analytics or data science. So we need to take data governance to a new level, and not just governance at the individual field level, but collectively as a data set. That is, as a cohesive set of data elements within a specific bounded context and business domain.
So let's look at inconsistent data sourcing. If you notice the image on the left, it is not the ideal way to data source. So all the boxes on the left of the non-ideal image are, you can see have dataset C, dataset B defined many different ways. On the top, source application, you have dataset B, purple, and then the next one, blue, red, blue, and then green. So now, as you look at all of your downstream applications, you'll notice that they're all sourcing dataset B differently, right? So the first downstream application is using a combination of the red definition of dataset B and then the blue definition of dataset B. And the second application is just using the blue. And then, further on down, it's green and red, and then red and purple. So you can see that all this different data sourcing creates an exponential amount more work. Preventing the creation of this type of a Kafka spiderweb is why the necessary upfront domain-driven design work should be done.
Right, and in contrast, the image on the right is the ideal. And here we see that each downstream app that requires the same business context uses that data set in the same way. The boundaries of each of the data sets, A, B, C, and D, are the same throughout each downstream app. And this takes us from inconsistent data sets to consistent for a given business context within its domain.
Now let's talk a little bit about inconsistent data derivation. Again, if you look on the left-hand side of the screen, the non-ideal image, you have one upstream app that has all of your data sets, and then if you look all the way at the right, you'll see our downstream apps are all deriving data set C differently. The correct way to derive it, and the way it should be done uniformly, would be C equals A and B, data from data sets A and B combined together. However, you can see our downstream data sets are defining C to be A and D, or A and E, or A and F. So they're all calculating data set C differently.
Right, that's right. So the scenario on the right is the ideal way to derive data, where the business meaning of the data is the same. For example, if C were to represent profitability and it's calculated based on the same formula across multiple consumers, you would want each system to treat dataset C in the same way, define C in the same way, and determine the sourcing of C in the same way.
Now let's move on to a little bit of a history of data segregation between applications. And if you look at the image all the way at the left, you can see a first iteration of breaking down the monolith into different microservices. And in this first iteration, you can see that that they're sharing the same database. So even though you may have broken out your microservices, you still have one shared database that see an order table and a consumer table, such as if you were doing an online ordering, shopping cart application, a nice Hello World example, right? They see those data sets in the same way, and there's one area where both of those microservices will always go to get those data sets. And then moving on to the image in the middle, you can see that in the next stage, the schemas are broken up. The data being sourced for microservice, for the order microservice is accessing its own schema, as well as the customer microservice. It is accessing its own schema, and everything is kept in sync back and forth through HTTP. And then, moving on a little further on in our evolution of breaking up the monolith into many, different components, you see that the order microservice and the customer microservice are communicating with each other over messaging. right? So there is an event, consumer, and publisher for each of those domains, each of those data sets. And so you sort of have that, that evolution, back and forth, which then brings us to, the next step of completely breaking down your monolith into, into domains, right-sized components, and having all of the pieces of each of those components together. So you can see on the left in the order domain, you have your order microservice. It has, in this order, your order domain has its own event store, its own read storage. It has its own event publisher, event consumer, event, and names of events that belong to that domain, its own endpoints, and they're all servicing that same set of data. Same thing with the customer domain on the right. It has its own set of microservices, endpoints, read storage, event store, etc. And the customer domain knows that it should only be getting order data from the order domain, and the order domain knows that it should only be getting customer data from the customer domain. So now let's move on to a little bit of how do we define these domains. A generic example, domain-driven design for a single application. And again, I'm going to stay with the example of a hotel booking system. As you can see, you have, for every actor, you have several use cases. So you work with your business to do this. They know their use cases, they know what they want to do, and they'll be able to tell you, for customer and for use cases, search hotel, you'll have input location, date, range, room rate, facilities, right? And then the output will be, hotels and availability. So your business, your product owner will be able to tell you that. And as you go through every single use case, you'll be able to see on the right, when you're drawing your bounded context diagram, that each of these inputs and outputs that I've been mentioning have their own rectangle. They're all connected up. They, a hotel has a rate, it has a location, it has facilities, it has a room type, right? And so as you connect these up, you'll be able to sort of see a pattern of where your domains sit. This part of it is an art and not a science as you connect these things up. And then to further define the boundaries of your data sets, you want to go through each use case, each complete transaction, and make sure that the boundary you've drawn around that, that particular bounded context doesn't have too many lines crossing between domains for each transaction. So you'd loop through and you would go through to make sure you're not hopping too many domains in each transaction. So that's how you would form these data sets. It's important that you work with the business so that you understand all of those data sets. And then you have your architects come in and say, well, how do you lay event storming on top of this? And you use the same table. You use your same domain-driven design use case table. And as you do this, you would just add these extra columns of event, command, and query. So you can see that, again, for our create customer or make a reservation or search for a reservation, there are events or commands or queries that will trigger this use case. So this is how you're going to start to draw your eventing into your architecture diagrams, particularly for your event storming table, which brings us to our eventing diagram. And I only did this for one of the use cases. So this is for the reserve hotel command. When a user comes in and does reserve a hotel, that acts upon the customer domain, which is not just the set of data that we've put together in our domain-driven design. It also includes events that are connected to that domain and the metadata. So a domain is not just sets of data. You want to make sure your events are all named the same way and acting upon the domain in the same way. So as you can see, as you go through this, our customer domain, when reserve hotel comes comes into this. A room reservation requested event is active, comes out of the customer domain and then goes to the hotel management, domain. Okay, and then from there, the hotel management, domain, sends a message to the card, the vendor, the card vendor domain, and the card vendor domain picks that up, and then the card vendor domain sends a payment process event to the reservation domain. And then the reservation, domain will then send a room reservation success event that will be picked up by both the hotel management domain and the customer domain. So you can see that those two components are reading from that same topic, right? You really want to make sure that this one message that is part of that domain is not repeated, and you're getting that data in the same way at the same time. So that is how you would include, eventing. So let me just go to the next. That takes us to enterprise, domain-driven design and how to apply it to the reuse of data sets.
Right. This leads us to how we can take domain-driven design beyond the single application approach and expand it for greater benefit across the enterprise. So while we want to have ubiquitous distributed data sets working in concert across multiple systems, this suggests some level of governance is also necessary to catalog the metadata about the data sets to really enable reuse when possible. So the practices of using domain-driven design throughout the lifecycle of data from producers to consumers can help us capture some important metadata about each bounded context and data set. So listed here are some examples of metadata. Like, for example, to take lineage for starters. Lineage is really important because it identifies the source of the data elements in the data set and includes any transformation rules that are applied. And sometimes this can be thought of as like system-to-system data lineage. It might also include some new data elements created as a result of calculations or transformations. And in this way, the data set is really described as a collection or a collective set of data elements. And then the business data owner is one of the core principles of domain-driven design because the business really should be ultimately responsible for the data, including who can access the data sets and ensuring that it's fit for purpose. And the business data owner is really someone who is a subject matter expert in their business domain. Now, the data steward is a role that manages the activities related to data governance in collaboration with the business data owner. So in many ways, they represent the data owner within that data governance function. And the technical owner sometimes can be confused with the data owner, but really it's important to note the distinction because the technical owner is responsible for the system that manages the data set. Interoperability is one of the most important aspects of data sets because it really describes how it can be related to and used with other data sets. And then distributions identifies how the data set can be delivered to a consumer. For example, APIs or events on a Kafka topic. Events on a data set need to have a ubiquitous language also, so we can communicate between components in a uniform way. So by using domain-driven design throughout, it's possible to manage the reuse of data sets across the enterprise from the producers of the data and the operational systems to the consumers of the data in the analytics applications. So how do we move from operational systems thinking to data ecosystems designed for analytics and other data consumers? Now, there's a lot of heavy lifting, as I like to call it, that goes on to take data out of those operational systems to make it fit for purpose in a way that people want to use it and analyze it. And this shows how a variety of data sets from multiple sources must be brought together and integrated, which involves going through many computations and functional transformations to harmonize that data into data products that are suitable for business consumers. So by leveraging domain-driven design from the operational source systems like we've been discussing here, we can continue to apply that domain thinking to our data engineering practices in the form of what we call a data mesh. And that is where each node on this mesh represents a business domain. So for example, thinking back to the domain-driven design for a hotel booking system, we can envision that a customer as a domain, as one of the data domains. And within that, there are data sets that make up that domain. And we build in the interoperability between these data sets and domains so we can ensure that we can combine the data sets into data products for downstream consumers. So this in turn helps to maintain the same sense of data ownership from producers of the data on the left to the consumers of the data on the right. And this will help us to promote better data consistency in the long run when the business data ownership is built right in throughout the ecosystem. So looking back on the past 20 years or so, as I've been doing for many years in the data world, and how we can have traditionally integrated data for downstream purposes such as reporting and analytics, a common practice has been to pull all this data together into one place, one warehouse, one big data lake. But in the effort to consolidate and integrate data, we created a monolithic data application in a couple of ways. Because by its very nature, this type of data monolith centralized the data ownership around a tech-focused, highly specialized team, which is often referred to as the data warehouse team. And as a result, this data monolith became a complex system of highly coupled pipelines, which of course became difficult to change over time and slow to respond to the eventual business changing needs. So by leveraging domain-driven design that has been applied to break up the monolithic operational systems, we can break up the data monolith into a data mesh that is also oriented around a similar domain-based approach. Now, this concept of data mesh, shown here, has been introduced in recent years by Zhamak Dehghani of ThoughtWorks and is described by 4 principles: domain-oriented data, data as a product, self-service data infrastructure, standards, and governance. So let's take a closer look at what each one of these principles means. With domain-oriented data, this is where we can leverage what has been done for microservices, as shown earlier by Laura, to decompose systems into services built around a domain-bounded context and applying this to data in the same way. Next, data as a product, again, carrying forward the product thinking that has been applied within our operational systems. There's no reason why we cannot. In fact, we should apply this to data as well. So the data mesh is an ecosystem of data sets, which can be consumed into data products to serve a variety of consumers. And as a product, it should be offered in a way that our consumers can find it, know how to use it, know the lineage, including quality and its fit for purpose, along with knowing what it is, how it is described. And I like to think of this as like the self-describing nature of products that we're familiar with in a store. Like in a grocery store, in fact, I can expect to find a list of the product's ingredients that describe what it is, and the nutrition facts are shown in a standardized format or syntax. So I think we need to find ways to characterize our data products in similar ways. This will help the data products to be consumed and owned by the business in a more engaging manner. Self-service data infrastructure. Well, to really break up the monolith, we should think about ways we can provide domain-focused teams with a common data infrastructure platform that is domain agnostic, one that can be utilized by independent cross-functional teams in a way to develop data sets without the overhead of a larger system, much the same way as microservices strive to do the same thing, independent but interoperable based on a set of core standards, which leads me to the last principle of standards and governance. In order for us to provide autonomy to the data domains, that is to break up that monolith, we must be sure not to create data silos. Therefore, it's really important to be able to establish standards of how these data sets can be combined across the domains to create meaningful data products. And this may seem challenging at first, and perhaps it is, but hopefully we can draw from the experience that we have with microservices to utilize a common set of practices in a similar way. And another important aspect of governance is access control, which should also be applied across domains and the data products to ensure the data products are secured according to the business owner's approved use for the data. So by applying Zhamak Dehghani's principles of data mesh and extending domain-driven design to break up data monoliths, we can achieve enterprise domain-driven design.
So to recap, we've covered advancing domain-driven design from one application and to enterprise domain-driven design, so that we can share our data sets across many applications and not not redo our work and have Kafka spiderwebs, and we can have a cleaner API strategy and real-time strategy throughout our enterprise. And we also can merge with the data side of the house, which is very important.
Right. And we can use the domain-driven design principles from operational systems to solve for similar challenges of the data warehouse or analytics environments in terms of breaking up those monoliths. And this will help to unify those operational and analytical worlds around common business-driven domains.